So for this video, we're just going to be going over the elementary derivatives. So in the first video in the series for like the essentials of pre-calculus, like I mentioned what like those elementary functions were, like the most basic functions that we're going to be looking at. And so in this video, we're going to be looking at like the power rule and derivatives of trig functions, logarithms, and the exponential. And so yeah, we'll get to that, and I'll just give like some tips on working with these. So uh, first things first is the power rule. So this would be for like our polynomial functions, um, and also like the like any like square root functions or the reciprocal functions too. So like anything with a power with an exponential, um, we have a pretty simple rule here for taking the derivative. That way we don't need to use the long definition of the derivative. And so that's just when we take d by dx, so the derivative with respect to x of x to some power p, this is going to equal p times x to the p minus 1. And so what the basic idea here is that we're just going to look at whatever power is going on and we're knocking it down as a constant in the front, and that power goes down by 1. And this is going to work with any power, like not just like the integers. So we'll look at like some examples here. So if we have f of x equals x to the 3. So what's the derivative then going to be? It's going to be f prime x, which again, so I'm just moving back and forth between the notation, like the Newton f prime notation and the Leibniz d by dx notation, just to hopefully make sure that you guys are comfortable moving back and forth between the two. The new notation's easy when you just have like that one variable. It's when more so we get into topics like implicit differentiation when there's different letters going on that could be variables. I find Leibniz notations much nicer to work with. But anyways, so the derivative of x cubed. So what we're doing is we're knocking that 3 down. So it's 3 times x squared, because the remaining power gets knocked down by 1. And this also works if we have a square root, right? So if we have g of x is the square root of x, well, remember that square roots, or any type of root, is just an exponential where the root we're taking is in the denominator of the exponent. So this is x to the 1/2. So when we take its derivative, we're doing the exact same thing. We're knocking it down. So we're going to have 1/2 as the in front, and then x, and now we're doing 1/2 minus 1. So that's going to end up being negative 1/2. Negative 1/2. And so when we have a negative exponent, remember that means it goes in the denominator, and the half exponent is the root. So this is going to equal 1/2 root x. And lastly, the last example with this right here that I want to emphasize is when you have these functions, these reciprocal functions. So if we have h of x equals 1/x. So anything in the denominator, that's a negative exponent. So this is going to be x to the negative 1. And we do the exact same thing when we take that that derivative is we get that negative 1 in front, and we knock it down, so we have x to the negative 2. And so this just becomes -1 over x squared. And from this power rule, we are also going to get the constant rule. So something is that whenever you take the derivative d by dx of just some constant, that's going to equal 0. And just stop and think about that. What does the derivative mean again? We talked about that in the last video. The derivative is a function of the rate of change. If you just have a constant, is it changing? No. So like the slope of its tangent line is always going to be 0. And so the derivative of that constant is 0. And we can see this with the power rule because let's say, what's the derivative of 7? Well, that would be the same thing as saying, what's the derivative of 7x to the 0? And so that 0 gets brought down, right? And that makes everything 0. But this point right here is the nice transition into the next point that I really want to emphasize, which is how the derivative can move through constants, constant multipliers, and addition. And so that's because the derivative is a linear function. All that means for here is that if we have the derivative of some constant times a function of x, then the derivative just moves right through that constant. We're just going to have that constant times the derivative of that function. And the other rule, the addition, is if we have the derivative of a function plus another function, and it equal the derivative of each function, the derivative of the first function plus the derivative of the second function. It distributes through the brackets, and so this is what it means for the derivative to be a linear function, is that it can move through constants and it can distribute. However, if we have like a function times another function, don't think that this means that the derivative is just going to be the derivative of the first function times the derivative of the second function. It's not. So that's going to be the next video where we talk about the different rules. So there's the product rule and quotient rules to deal with that. This is just when we have addition. And so I want to walk through like some examples of what this looks like. And so right here, if we have what's the derivative d by dx of 6x squared. So this 6, this constant in front, it just moves right through that derivative. Because again, think about what it means to be like what the derivative is. It's that rate of change. And so if this whole function is just times some constant, then its rate of change is just going to be times that same constant. And that's really clear when we look back at that limit definition of the derivative. If we have that f of x plus h and that f of x, if they both have the same constant in front, that just factors out in front. And so this moves on right through. So we have 6 d by dx of x squared. And now we simply apply what that last rule was. So we knock that 2 down. But since there's already a 6 in front, it just gets multiplied by 2. And so that gives us 12x, right? Because the exponent goes down by 1. And so like, let's just look at another example now, d by dx of x cubed plus 4x squared minus 6x plus 1. And so So just like right here, the derivative is just going to be acting on each term individually, each new thing that we're adding into this. We're just going to take the derivative of them one at a time and keep that same sum. So when we take the derivative of this first one, we're going to knock that 3 down, and so we get 3x squared, right? So we're just knocking that 3 down and we're lowering the exponent by 1. And now let's look at this next one. Plus, so there's that 4 in front, so the derivative moves through it, and it's going to be times that 2, so plus 8x, because that's the 2 minus 1. And now, again, we're going right through that 6, so minus 6, the derivative of x, is just going to be 1, right? Because when we get x to the 0, that's just 1. Um, so this will just be minus 6. I'm just gonna write that down in case I said that a little confusingly. So d by dx of just x. So what's the rate of change of a straight line? Is just going to be some constant number, right? And so like this is like x to the power 1, so that 1 gets knocked down, and then you get x to the 0. But x to the 0 is just 1, so this is just 1. So that's all I was saying there. Yeah, and then so now plus this constant, so this is 1, so that's kind of like x to the 0, so that 0 gets to knock down, so that's just 0, so it's just plus 0. The derivative of a constant is nothing, it's 0. And so yeah, and so this is like the main idea here. It's just keep in mind that derivative, when it comes to a constant just on its own, it's 0. But when it comes to a constant times something, it moves right through that constant. And so that's really a point I want to emphasize, that some people get kind of stuck on. And that's why I kind of mentioned, like, if it helps you, if there's no x term, then you just think of that as x to the power of 0. If that helps, like understand why, or again, just think about what it means, what the derivative actually means. And so if you just have a constant, then that's not changing. So its derivative is going to be 0. And if you have a constant times a function, then the derivative is going to have that same constant in front. So yeah. The next thing we're going to look at is just the trig functions. And so there's really only 2 that you actually need to like fully like commit to memory, and that's just the so the derivative d by dx of sine x is cosine x, and the derivative of cosine x is negative sine x. So just remembering that the derivative of cosine, we're gaining this negative sine x, and the derivative of sine is cosine. That's really like the only ones that you need to remember, because it's true that the derivative of tan x is secant squared x, and you know, like you're gonna remember this just by like working through it. But the thing is, if you don't memorize it, you can always derive this. So in the next video, we're going to be talking about like the quotient rule and product rules and things like that. So you can always just rederive. So if you don't remember that the derivative of secant is tan secant, and the derivative of tan is secant squared, that's fine if you don't fully like remember that. These are the ones that's important to remember, and you can always just like if you're on a test or doing an assignment, you can always just rederive the rest. It took me actually a long time to remember the derivative of tan with secant squared, just because like when I first took this class, I just knew, okay, I'll just remember to use, you know, the chain rule or the quotient rule and rederive it. But you don't always have to. Right here, yeah, the main thing to remember, sines, derivative of sines, cosine, derivative of cosine is negative sine. And I'm just gonna show that visually. I'm just gonna draw a graph real quick to hopefully give like an intuitive understanding of that. That keeps repeating periodically. So this is sine x, and we'll do cosine. And so just look at how it's changing right now. So so if I zoom into like that very first spot, if I want to emphasize this right here, what's happening to sine? This is like the highest slope that sine has, and it's in the positive direction. And and so we know that cosine is at its highest right there. So that kind of makes sense that um, like if you're forgetting which one has the negative sign. So it makes sense that the derivative of sine is going to be cosine right there, right? And then likewise, if we look at cosine right there, it starts at 0, like with its derivative, and it's going to be moving downward, so it's going to be becoming negative. So we see that it's going to be the negative sign. Um, so hopefully that helps kind of keep that straight. And then the last elementary function that we need to remember is just the exponential. This is a super easy one, exponential. Uh, and it's just that the derivative of e to the x is e to the x. The derivative of the exponential is itself. And so when we think about what that means again, so what is the rate of change of the exponential? Well, it's the exponential. Like it's describing its own rate of change. So that's the whole idea there, is that it's the derivative itself. And then for its inverse, d by dx um, of ln x is just going to be 1 over x. And so that's really what like these are really just what you need to remember from this basic the elementary function. So the roots, the powers, the reciprocals, those are all described with this rule. The trig functions, you just need to remember that derivative of sine is cosine, derivative of cosine is negative sine. And for the exponentials, the derivative of e to the x is e to the x, and the derivative of ln is 1 over x. That's really all you need to remember. With the exponential, if you have a different base, you just kind of want to get it into this form. So for example, if I say, what's the derivative of 2 to the x? Well, we know that e and ln are inverse functions, right? So when they're inverse functions, that means they cancel each other out. So we know that e to the ln x is just x, because the e and the ln cancel each other out. Like that's what the inverses did. Like we talked about this in the first episode on the essentials of pre-calc. And so all we're going to do is we're going to say e to the ln 2. Well, that's 2, because again, the e and that ln cancel out. So what we're going to do here is we're going to replace that that 2 with just e to the ln 2. And this is to that power of x, but when you have an exponent to another exponent, you can just bring it down. So this is just d by dx of e to the ln 2 x. And I'm going to give you a little taste of what we're going to be doing in the chain rule, which when we have that constant in front, all we're doing is we're bringing that constant down now. So it's just going to be ln 2 times e to the ln 2 times x. And I explained this step in our video on the chain rule, but just something to keep in mind that's derived from that chain rule is that whenever you have that constant right next to the input, you're just going to be bringing it outside. So it'd be the same thing if we have what's the derivative of sine 2x. That's going to end up just being 2 cosine 2x. Yep. And just this last step up here is we replace this e to the ln 2 back into 2. So we end up just getting ln 2 times 2 to the x. And so the derivative of 2 to the x is just ln 2 times 2 to the x. Yeah, I hope. Yeah, so if this is an area that maybe you're making like some mistakes on, you're like, okay, like why is this not working out? I hope that this video was just a nice simple and clear explanation for these elementary derivatives and how you work with them. If there's any questions, comment, let me know, but I'll see you guys next time.